this is module 29 of the course on econometric modeling. We have been discussing univariate time series model, and under that in the last module I had discussed modeling trend, and in this module I am going to discuss seasonal variations or modeling seasonal variations or seasonality. So, now focusing on seasonal variations. First of all, we would be defining seasonality. If a time series is observed at monthly or quarterly intervals or even weekly or daily, it may exhibit seasonality. So, whenever there are very explicit clear cut variations in the data observed just because of a change in the frequency of observation, then that can be ascribed to the seasonality component. For example, certain products are more in demand in certain seasons and their prices are also higher during those seasons. Alternatively, when supply varies seasonally, then we can expect prices to be lower when supplies are higher and vice versa. So, even if we do not talk about prices, we can understand that for certain products the demands are higher in certain seasons. For example, during the summer months, we would find that the demand for AC, fans, coolers, etc. will be higher. Similarly, during the winter season, we must be observing demand for room heaters to be higher and other appliances which provide us heating services, maybe even electric kettle, the products which are used for either heating air or water. So, as a result of which we can observe seasonal variations. So, these variations which we are observing in the demand for a particular product is not due to a change in income, change in prices or something. It is just because the time of the year has changed. So, the season requires a different kind of appliance, right, and that is why we ascribe it to seasonality, seasonal variations. So, one way to model this phenomenon is to allow the expected value of the series y t to be different in each month if we consider monthly data, or each quarter if we consider quarterly data, and so on. As another example, retail sales could be typically higher in the fourth quarters of the financial years. By financial year I mean the year starting from April and ending on 31st of March every year. So, the last quarter is January, February, March. We can expect a higher retail sales during the last quarter. Maybe because of the closing of the years when most managers try their best to meet their targets. Retail sales may also vary with festivals. For example, it is very pronounced in the Western economies that during Christmas the retail sales actually increases there, and similarly in our country we can expect an increase in the purchase or demand for jewelry, gold products as well as garments during certain seasons when marriages take place, and then also during the festivals like Diwali, Holi, we can expect increase in the increase in certain goods of consumption, increase in the demand for certain goods of consumption. Again, this can be captured by allowing retail sales to vary over the course of a year. So, this is how we generally could incorporate a seasonal variations. Even though many monthly and quarterly data series display seasonal patterns, not all of them do. For example, there is no noticeable seasonal pattern in monthly interest or inflation rates. In addition, series that do display seasonal patterns are often seasonally adjusted before they are reported to public use. A seasonally adjusted series is one that in principle has had the seasonal factors removed from it, and we work with a seasonally adjusted series. So, some process or methods, some rudimentary or basic process of deseasonalizing a data will be discussed in this module, but then there are other programs also available which automatically deseasonalize a series or a set of data. Seasonal adjustment has become so common that it is not possible to get seasonally unadjusted data in many cases in some of the countries, specifically if we can talk about US data. Sometimes we do work with seasonally unadjusted data as well, and it is useful to know that simple methods are available for dealing with seasonality in regression model. Also, another problem is that having a seasonal component, the seasonal component actually explains certain variations in the dependent variable. So, removing the seasonal component is actually losing out on some information. But of course, if we are not interested, we know very well that the data exhibits some seasonal patterns, and if you are not interested in understanding estimating the seasonal patterns, then the seasonal variations can be removed, and then we work with the seasonally adjusted series where we are more interested in examining the impact of other factors on that particular variable. So, generally we can include a set of seasonal dummy variables to account for seasonality in the dependent variable, the independent variables, or both. The approach is simply to allow the mean of the series to vary across seasons. Suppose we have monthly data, and if we expect the seasonal patterns to be roughly constant within a year across time, then the model is formulated as having 11 dummy variables for 11 seasons like February, March, April, May, June, July, August, September, October, November and December. Other than that, I am also including some of the independent variables like xt1 to xtk. We may include independent variables, we may not, but for generalization I am including some independent variables, and we have one constant term which is measured by the parameter of which is measured by the coefficient beta naught, where February t to March t to December t are dummy variables including a particular month for a time period t. Alternatively, February t will take value 1 if t corresponds to the month of February in any year, otherwise 0, and similarly the dummies are constructed for the other months. Therefore, for a time period t, only one seasonal dummy will be equal to 1, all others will be 0. So, there is an example of seasonal dummy variables. What I have considered here is IIP general. I have taken the data from India. The data is actually long up to 2020-21 July, but I have truncated it here because I just want to show here how the data seasonal dummy variables are included. So, here the first two component 2015-16 refers to the financial year and the last component refers to the month. So, 4 here refers to April, 5 May and so on. So, you can see that we are not also including, or I have not included any other independent variables also, and the constant term need not be included because most packages automatically report the parameter estimate of a constant term. If only we do not want the estimate of a parameter constant term, or if we want to exclude the constant term, we can specify that in that regression package, and accordingly that will be removed, but otherwise this is the default setup. So, we are actually having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 dummy variables. Starting from April, 4 is month of April. So, April is having 1 here, for the rest of the months I am having 0. Similarly, this is May. So, again for May I have 1, for the rest of the month it is 0, and you can see that the same thing is being repeated here, again 1 for April, 1 for May, 1 for June and so on, right. Note that in the formulation in equation 1, January is the base month and beta naught is the coefficient for January. So, since we are considering 11 dummy variables and there are 12 months, so we are not considering the 12th month. Instead, there is a constant term, and the constant term actually corresponds to the parameter estimate of the coefficient of the dummy which is not included or mentioned explicitly. One can either include dummies for all 12 months and no constant term, or 11 dummy variables and one constant term, which we have just done. Because if all dummy variables are included along with the constant term, there will be the problem of perfect collinearity and estimates will not be possible. As we can understand that if we have all 12 dummy variables here, for example, if I have also the month of March either here or here, then what happens is that, and if I sum all these 11 all these 12 columns, then that will also be equal to 1. We already have a constant term having all observations equal to 1. Then the sum of these 12 dummies will also have all observations equal to 1. So, there will be the problem of perfect multicollinearity, and as a result of which estimates will not be generated because estimates are not unique. These problems have already been discussed in a previous module. So, likewise for quarterly series, one may include dummy variables for 3 quarters and a constant term, or 4 dummies for 4 quarters and no constant term. A model of the form expressed in equation 1 can be estimated using OLS. If there is no seasonality in YT, then once XTJ, that is the dependent variables, have been controlled for, then delta 1 through delta 11 are all 0. Delta 1 to delta 11 are the coefficients corresponding to the dummy variables, right. They would all be 0 if there is no seasonality. This could be easily tested using an F test. So, we can go for a restricted regression and an unrestricted regression. So, where the restricted regression does not include any dummy variables, seasonal dummy variables, and the unrestricted regression actually does include the original model as expressed in equation 1. Now, here XTJ refers to basically the jth variable. There could be k independent variables. So, j equals to 1 to k, and t basically refers to a particular time period. So, for all the k variables, XTJ refers to the tth observation for any of those k variables. As mentioned above, that in equation 1 there are only 11 monthly dummies where January is excluded, and therefore, beta naught, the intercept actually is the coefficient for January. Therefore, beta naught is the seasonality of the omitted season. So, if we rewrite equation 1 by including the January dummy as well. So, now instead of having a constant term, I am having actually all the 12 dummies. Then equation 2 does not include any constant term. This is equation 2, and the explanatory variables are also excluded just to keep the exposition simple. Because even if I exclude the independent variables, the following discussion is actually not going to be any different. So, now you can observe that beta naught is equal to gamma naught. Beta naught is the original intercept, is now equal to gamma naught, and delta I, that is the coefficients associated with the dummy variables, is actually gamma I, that is these coefficients, minus gamma naught, where I stands for 1 to 11. So, delta I, that is delta 1 would be gamma 1 minus gamma naught. Delta 2 would be delta 2, that is in equation 1, delta 2 would be gamma 2 minus gamma naught, and so on. This implies that delta I in equation 1 measures the difference in the seasonal component from the reference season. So, now basically we are trying to get into the interpretation of the coefficients of the seasonal dummy variables. What it says is that the coefficients of the seasonal dummy variables, which are there when we do not have all 12 dummies, but rather when we have 11 dummy variables and 1 intercept, then the coefficients of those dummy variables measures the difference in the seasonal component from the reference period. For example, here the reference period is January. So, now I take up an example of seasonal series, again working with monthly IIP manufacturing series for 2015-16 April to 2020-21 March. In the Indian context, most of the data are reported for financial years, that is from April to March, and that is why though the original equation had calendar months like January, February and so on, this example I am considering, in this example I am considering periods like starting from April. So, as you can see that this graph very explicitly shows that there is seasonal variation in IIP manufacturing. these peaks correspond to March of every financial year. So, this is like 2016-17 March, this is 17-18 March, this is 18-19 March and so on. So, in each and every year the IIP manufacturing, Indian IIP manufacturing series reaches its peak, and then after March there is a sharp drop every year. So, there is very clear seasonal pattern, right. And then after March, after April again there is an upward movement, there is a downward movement. Most often you would see that there are ups and downs on a continuous basis. Now, there are certain seasons where not much variations are actually observed, right. For most part it is possible that not much variations are observed during certain seasons, but the prominent differences or what pronouncedly come out is that in March it reaches a peak, and all through the year, I mean across all the years, the month of March records the maximum increase or the highest figure for Indian IIP manufacturing series. Okay. And similarly, April almost corresponds to the lowest values of the series, but then there are also other months when it is actually somewhat equal to April, but March is actually not matched by any other month in terms of the values of the series. We also observe that there is a broad upward trend. Now, this broad upward trend implies that there is also a trend component, right. Another thing I just would like to mention that I have considered data till 2020-21 March, because after that there was a sharp drop in the IIP manufacturing, and it was very low. As you can see that it went up to this level and it was actually further down. It came below 100 for 2 months during 2020-21, most probably in July-August. So, for 1 month the figure was 53, the another was 79. So, because of these outliers, that is extreme observations which are not getting well coordinated or well aligned with the rest of the series, when I run a regression including those observations, my regression results were very poor. But the moment I excluded those extreme values and truncated my data at 2020-21 March, I actually had a very nice regression results. So, these regression results, I had 2 alternative models and they are reported here. First of all, I have considered the reference period March, and then the variables are the coefficients and their standard errors, t values and t statistics are reported here, along with an estimate of a time trend, deterministic trend. You can see that all the p values are very small, which implies that all these months are actually significant. So, they are significantly explaining the variations in the original series, that is IIP manufacturing. And since we observe that March always has the highest figures or values, as a result of which, that is reference to the base period, all the months are having basically negative coefficients. All the coefficients are negative because reference to the base period, the values are all lower, right. And you can also see that in fact April has recorded the maximum or the lowest value, maximum negative number or the lowest value, and the intercept which actually measures the coefficient of the intercept term is actually very high. The t statistic associated with it also very high. The time trend or deterministic trend explains nearly 36% of the variations in the dependent variable, holding other things constant. Fair enough. We also have observed the very good R square value, which is 91%, and adjusted R square value at 88%. Now, I have re-estimated this model with April as the reference season. So, first that was the season March, which had the maximum, which reported the maximum figures for IIP. Now, April used to have the lowest figures for IIP. Now, you can see that against April, all the other months are actually having coefficients, positive coefficients, which implies that reference to the base periods, all the months are having positive contributions to the variations in the dependent variable, and March is actually having the highest value among all other months. Again the t value explaining roughly 31%. You can see that against April there are 2 months which are insignificant, not 2 months, rather there are quite a number of months like 30 starting from June, July, August, September, October, November. All of them are having insignificant values, implies that with reference to the base period their contributions to the dependent variable is not statistically significantly different, right. Here the R square value is somewhat lower, 66%, adjusted R square value is at 57%. Okay. So, this is how if we change the reference period or the base period, then we can observe differences in the seasonal or coefficient estimates of the seasonal components. This is because the seasonal components actually measure its contribution to the dependent variable with reference to the base period. The difference between its contribution and the reference period actually is getting reflected here. Now, we talk about how we can deseasonalize a time series. This is very similar to the process of detrending discussed earlier. Suppose the original model is of the form yt equals beta naught plus delta 1 February t to delta 11 December t, beta 1 xt1, beta 2 xt2 plus ut. So, my original model. The OLS slope coefficients beta 1 hat and beta 2 hat can be obtained as follows. Regress yt, xt1 and xt2 on a constant and the monthly dummies February to December, and save the residuals say yt tilde, xt1 tilde and xt2 tilde. For example, the regression equation for yt will look like something like this, and this is actually the equation 3 excluding the independent variables, fair enough. So, this is my equation and I collect the residuals which is denoted by ut hat, also can be denoted by yt tilde, refers to the deseasonalized yt, and then this can be done for the independent variables also. So, this is one method of deseasonalizing a monthly time series. A similar interpretation holds for xt1 tilde and xt2 tilde, and after that we run the regression without the monthly dummies of yt tilde on xt1 tilde and xt2 tilde. This gives us beta 1 hat and beta 2 hat, which we would have otherwise obtained from this equation 3. In some cases, if yt has pronounced seasonality, a better goodness of fit measure is an R square based on the deseasonalized yt. This nets out any seasonal effects that are not explained by the independent variables, that is xij or xtj. Time series exhibiting seasonal patterns can be trending as well, in which case we should estimate a regression model with a time trend and seasonal dummy variables, that the one that I have done in the example that I just showed you. The regression can then be interpreted as regressions using both detrended and deseasonalized series. Essentially, we detrend and deseasonalize yt by regressing on both a time trend and seasonal dummies before computing R square. Now, we actually sum up whatever we have discussed in terms of while discussing univariate time series modeling. So, traditionally a time series can be decomposed into a trend component, the deterministic trend upward or downward, cyclical terms, seasonal terms and a disturbance term. Therefore, a series can be written as yt equals tt, the trend, zt the cycle, st the seasonal component, ut the disturbance terms. While the trend and seasonal terms are assumed to be deterministic functions of time, that is they can be predicted with 100% accuracy, that is their respective values at some future time t are known at any lagged time t minus d, which is d units of time prior to t. The cyclical and disturbance terms are actually random terms. Further, as we know that the disturbance terms are residuals or unexplained, Cycles can be modeled using autoregressive processes as discussed in modules 26 and 27. So, if you remember in modules 26 and 27, we had actually discussed that autoregressive processes or autoregressive moving average processes, they actually show cyclical patterns. So, cyclical patterns and disturbance terms are non-random, but disturbance as the term itself implies that they are most often, or they are supposed to be white noise processes, they are not explainable. So, we focus on the cyclical component, or cyclical components can be actually modeled. Therefore, a full model consisting of the trend, seasonal and cyclical components could be written as y equals Tt plus St plus Ct. Now, Ct is actually the original Zt in the previous slide, where Tt is the trend term, which is mu plus gamma naught t. Mu is the constant term, that is constant mean. T is the deterministic trend term. St measures the seasonal some dummy variables, or St measures the components having seasonal impact. So, dit refers to the seasonal dummies, and therefore, there are S seasons. So, we are actually having S minus 1 dummy variables, because we have already included one constant term here. Ct is actually written as an ARP process. So, an ARP process will be having a either monotonically, geometrically monotonically decreasing cycle, or maybe if there are some positive numbers, some negative numbers, then we will be finding oscillating decay. So, this implied that the regression is a complete regression model estimable using OLS, where the complete regression model looks like mu, the constant part, this is the deterministic trend, this is the seasonal component, and this is the cyclical component, plus this disturbance terms. So, that actually this is how we can decompose a time series, we can estimate its individual components either together or in consonance with each other, and that is how univariate time series can be modeled. Each and every one of its components can be modeled. This brings me to the end of the discussion on univariate time series model. These are the references that I have followed. Next, I will be taking up categorical variables, or variables having multiple categories for both independent and dependent variables. Thank you.